Hey everyone, welcome to Cassandra Lunch, or sorry, Data Engineers Lunch number 59. Today's topic is going to be on Spark tasks and distributions, and our guest speaker for today is Obi. He's an engineer here at Anant, and Obi will talk about how Spark splits up and distributes the work between nodes. And we'll also take a look at some example code in the Spark UI and also see how it's distributed as well. The co-organizers for the event are Rahul and myself. We are looking for guest speakers as well as sponsors. So if you're interested in giving a talk, either here at Data Engineers Lunch or Cassandra Lunch, feel free to reach out to me. My email is listed below. We are part of Data Community DC. Data Community DC believes in building a inclusive culture. So no matter your race, gender, sexual orientation, everyone is welcome, and we expect the respect to be given to all. Data Community DC is built up of a bunch of different organizations. We fall under Data Wranglers DC. So if you're interested in the various events Data Wranglers DC hosts, feel free to check out their website as well as all the various different events. So what do we cover here at Data Engineers Lunch? We cover everything that is data engineering, tools for data engineering, processes, so ETL, ELT, data wrangling in general, data cleansing, et cetera, from the ingress to egress processes, and all the various tools and software and technologies that are out there related to that. If anyone's new, feel free to drop a hi and hello and what you do with data engineering in the chat, as well as if you're watching directly on YouTube, feel free to drop that in the YouTube chat as well. Group rules, if you have a question, please ask it. Be polite and courteous to others. The guest speaker may have a specific preference in terms of questions. They may prefer it in the chat first, or they may prefer you to speak up. Usually the guest speaker will declare their preferences as they take over. And again, this is meant to be a community, so please do share what you know with us. Here at Anant, we design, build, and manage global real-time data analytics platforms surrounding Cassandra, Spark, and Kafka. So data engineering and ETL is a way of life for us here at Anant. DataStax is a partner and a sponsor. GW University also helps provide in-venue space when we have in-person events. We also have some organizational and institutional sponsors. If anyone has any announcements, jobs, if you're looking for a job or have a job, you can drop links in the chat on YouTube and Zoom, and we'll get them transferred over to back and forth, as well as any meetups, hackathons, conferences, or classes you want to advertise. DataStax Astra has a build-a-thon going on. The first month is wrapping up, but with each month, there's 3 months of challenges, so 1 round per month. So you can sign up for month 2. And then the top 3 winners of each round qualify for the demo day. And then there's prizes and swag to be won at each month/round. So if you win prizes, if you're in the top 3 of this month, the next month, you can also qualify for the grand finale prizes as well. Anant is hiring for full-time or part-time data platform operators, engineers, or architects. You can find out more at careers.anant.us. More events. Data Engineers Lunch happens every Monday at 12 Eastern, as well as our sister lunch, Cassandra Lunch, which happens on Thursdays at 12 Eastern currently. You can find out all of our events at anant.us/events. And with that, we will go ahead and hand it over to our speaker for today, Obi.
Hello. So as you heard, my name is Obioma Anomnachi. I'm an engineer here at Anant. Currently giving today's Data Engineers Lunch on the topic of Spark tasks and distribution. We're going to be looking at machine learning examples to sort of investigate the way that Spark distributes work in between nodes. I generally prefer to take questions via the chat, especially if we are in the middle of a section where I'm going through slides. But if we are in transitory sections, moving from slides to the demo or moving from demo to the outro, those are good times if you would like to unmute yourself and ask questions directly. I will be relying on coworkers to direct questions that come in through YouTube chat to Zoom chat where I will see them. So if you're on YouTube, just be aware of that. So like I said, today's topic is Spark test and distribution. We're going to go over a fairly somewhat technical look into the Spark internals of how that works. And then in the demo, we are going to open up the Spark UI and look at, well, stages, and tasks, but we're going to look directly at the way that Spark is splitting up some of these examples. So let's get started. All right. So first, we're talking about the architecture. So your top level that you have in Spark is your cluster level. It's a number of JVM nodes. They can be driver nodes, they can be worker nodes, and they together coordinate and execute all the processing data that takes place on the cluster. And then a task, which was mentioned in the title, is the smallest unit of work that gets distributed. Sorry, that's a typo. Distributed to worker nodes. And tasks consist of a single operation like map or filter that gets executed on a single partition of data inside of a worker, which we haven't really talked about yet, or an executor. Tasks run on individual threads within that process. And you take a sequence of tasks as long as they can all be run in parallel without redistributing your data, and we call that a stage. And then if data does need to be redistributed between nodes, you take a number of stages and you line them up, and that becomes a job. Operations that go across data partitions, things like count, things like for each, as long as they're happening across partitions, are actions that will happen on the job level, whereas something like map or filter will happen on the task level, and then combinations of those smaller tasks combine to make a job, a stage. So later on, we're going to actually look in the Spark UI. For running tasks, you can easily see the makeup of the individual stages. And you can also potentially set up the history server to look at them for the Spark history server to look at them for past jobs. It does not automatically show. All right, so shuffle operations, they come up when work is distributed in Spark because they're the part that specifically involves redistributing your data across the cluster. So it starts in some data configuration. Data is split up into partitions and divided between nodes. But each node has a copy of the full jar. So it has your code. It could theoretically run any individual task on that partition, but sometimes the partition is wrong. So since this operation involves data being copied and shuffled between executors, between machines, shuffle operation can be a costly one in terms of network traffic and also in terms of time and processing power. Shuffle operations can be caused by things like repartition, which redistributes data according to your own specifications. Things like coalesce, which gathers data from multiple partitions. Join operations, and by key operations like group by key and reduce by key, which basically split up your data in a new way. Shuffle includes elements of disk I/O, data serialization, and network I/O. Generally, Spark likes to work in memory, but if any of your data is on disk, then it needs to be redistributed and sent from one to another. Read from the disk, written to the disk, et cetera, et cetera. And if you look more deeply into it, the shuffle operation is actually set up. I don't think I have this tab open at the moment, but the shuffle operation is set up like a MapReduce program. So the lineage sort of goes MapReduce, Hadoop, Spark. And inside of the Spark internals, there is a shuffle map task and a shuffle reduce task. And you can get both of those, and that's how shuffle operations are performed. They just take and organize your data and then aggregate it from across the cluster. So rather than move on to the demo, first we're going to talk a little bit about the machine learning examples that we're going to look at. So today we're talking about neural networks or multi-layer perceptrons. They're somewhat interchangeable, not entirely. But basically a neural network has, one of these actually has a good picture. Here we go. Layers of nodes that are connected by edges, which have weights. So essentially your data comes in on the input layer, your X1 through whatever. And as you move deeper into the network, it gets your data points each get multiplied by your weights, added to your biases, and that creates your hidden layers or your middle layers. You can have only an input and output layer. A neural network with no hidden layers is certainly possible. But in this case, we're going to have a 3-layer neural network that we're going to look at for a little bit. And essentially, the process of training your neural net is setting these weights and biases so that your output layer has good accuracy. And we'll look a little bit at the math of that later. We have this sort of description of it. You can see the same weights for this layer, data, biases for this layer, and then it feeds into the next layer where there's some function on that, and that's your new data, which goes to the weights of the next layer and the biases of the next layer, and so on and so on. And this F here, intermediate layers, they use the sigmoid function for that. It's a function that goes from 0 to 1. So very negative numbers all get assigned very close to 0. Very positive numbers all get assigned very close to 1. And numbers in between 0 and 1, basically, ones near 0 get like actual distinguishable values. So like 0.5 happens exactly at 0. And then the output layer generally has a different logistic function that it runs on the outputs. And here's the one that talks about back propagation. So like I said, the process of training your neural network is about making sure that your accuracy is good. What you do essentially is minimize a loss function. So you have a loss function. In this case, they're usually things like root mean squared error, or maybe just simple error. You know, what is your actual value minus what is the value you're getting out of your neural net at that moment. And you use that to construct a gradient in as many dimensions as your input layer has. You then calculate the derivative of that gradient and then move along it in increments in order to train your neural network to minimize that loss function. So the name for that process is gradient descent. It's an artificial intelligence programming tactic, I guess, but it's not machine learning in and of itself. But when combined with a neural network, you can learn from your input data and create increasing performance over time. Yeah. So we're going to look at 2 examples in a little bit. The first works on the MNIST dataset, which is shown off here. It's handwriting recognition, although really anything that has 10 classification categories and images that fit into this, 28 by 28 size. So I've done classification on, fashion version of the MNIST data set where it's, coats, hats, bags, et cetera, and you have to classify those into categories based off the pictures. But the classic one is handwriting recognition. Because we're going to look through the code a little bit to sort of try and predict what exactly, what sort of distributions we might see in our, once we have these things running in Spark. So we're taking this one, which is a Spark submit of a ParSpark file, which does training of this this custom neural net. Essentially, when we look at the code later, we'll see that it basically uses a bunch of map functions. So it goes from input to layer 1 value to layer 2 value to et cetera, and then on to loss function, and then on to derivative loss function, and then on to back propagation step, et cetera. Just a series of maps that eventually get you to your value that you're using to update for the next round of training. So these things generally work in epochs. There is a variable called alpha that we'll see somewhere that determines how much you actually want to change on that gradient. Basically, if it's too high, you will overstep your local minimum of error. So you'll get worse performance. It'll take much longer to settle. So we generally take pretty small back propagation steps. So the derivative is calculated and it's multiplied by, say, 0.1 or 0.01 or 0.0001. And the smaller those steps get, the more sure you can be that your process will lead you to a local minimum. Because the derivative in that place won't tell you to go anywhere, essentially. And if you are moved out of that, there's something called stochastic gradient descent, where you sometimes just reset position randomly, which basically helps ensure it doesn't ensure. It's not like 100% guaranteed that you will reach your global minimum that way, but you get a better chance, essentially. But essentially, with smaller back propagation steps and more training epochs, you can get higher performance out of the same sort of model without changing the number of hidden layers or the number of neurons in the hidden layers or anything like that, which mostly determine how well your neural net ends up approximating whatever function is trying to approximate. And these generally aren't things that are calculable by human hands. Like I said, these images here are all 28 by 28, which means it's a 784 dimensional space that you're doing your back propagation in. Not something you want to sit down and do on pen and paper. But luckily, computers excel at doing the same thing over and over and over again. And then we are also going to run a quick example using the multi-layer perceptron classifier that's included in Spark MLlib. And we'll see how that sort of differentiates in processing, how that processing looks different in terms of how the Spark tasks are split up. All right. So now one more last thing before we get into the actual, before we start looking at the Spark UI for this, is we're going to look a little bit at the code. So here's the one that does MNIST. They have a custom, well, basically what they're doing, they have a separate Python file here that gets data. Basically, Keras or sklearn or something has a version of this data included in the package, which they download and save to CSV. And then later on, what we do is we take these images and we use them to train the neural net. So we have our split here. Basically, you can see it split into images for testing, images for training, labels for testing, labels for training. And that's where we can see sort of the first stage split that we expect. So loading data from a text file can be done in an individual task. But since to get all of your training data or all of your testing data, you need to load from 2 different files, there is a join command that'll be happening there. And we'll probably see that that's where the stages split. So we can expect stages to split when joins happen, like was mentioned earlier, or when the partitions are distributed badly. So for 1, a join will happen. And then for 2, we don't know if the labels and the training data would necessarily be on the same node. So those would have to be combined. So what's in this file is a function that applies an activation function to a node, a sigmoid function and sigmoid prime function, 10h function, 10h prime. All of those they're either activation functions that go on the output of nodes, or they're used for backpropagation later on. And then it does forward propagation and prediction with your neural net, computing the derivatives in your error function. And then stuff here that gets metrics using the sklearn library that they have made available for that. And then if we scroll down, so these aren't actually used, they're all folded in down here. But you can see that your forward propagation step is a map using your weights and your input data, essentially. And then here you can see that what's actually happening when you train in RDD is that you get some data, and then you map, you do your forward propagation for a couple of steps. You put it through your activation function, maybe a 10H, and then you get your derivatives, and then you do your back propagation step, which is a reduce. So this is a bunch of map steps and then a reduce step, but it's all happening on a single partition of data. So we expect to see when we look at the task, the way that this is split up later on, that it'll be inside a single stage, linear or parallel. So all contained within a single stage and not split up between stages. And then for the MLP classifier, if we look at the data for that, which is in this churn modeling, it has 1, a lot less dimensions, and then 2, the labels are all also contained within this file. So there's no join that has to happen. So we might expect to see that where the previous one splits between stages in order to do the join, this one is all contained in a single stage or less stages. All right. So we have a Spark cluster up. It has 2 workers running. Unfortunately, this isn't really going to be a showcase of how stuff is distributed, because even though we have 2 workers running, the Python script that we're using, and then we also have a Scala script that we're going to use because I had trouble packaging it into a jar. And those run mostly on the driver node. So we're not going to be able to see it splitting data up between nodes because there's really only the one where stuff is being done. All right. So Spark UI, make sure we're looking at that. Here we go. This is our Spark UI. And then we are going to run the first. All right, so this command, essentially what we're doing is Spark submit. it's all stored here because it's not on path at the moment. We have our file, main.task.py. We have our 4 sets of input data. MNIST images train, MNIST labels train, MNIST images test, MNIST labels test, and then we have a defined location to put output. So this program actually saves a bunch of information about your the efficacy of your model over time, essentially. And we can start this running. Basically, it just means that it needs an output. All right, we started actually running here at the bottom, still loading in the data. All right, starting the training loop. So in a little bit, we'll see the results of the first epoch. It will be pretty bad at identifying these digits. So the way that we generally initialize neural nets is that you put basically random values in for your weights and biases because you don't really know what they're going to be. And the idea essentially is that random is better than all zero because it takes a long time to move away from all zeros with a derivative. So starting with random data loaded in, it's much easier to do a couple of training loops and get something usable than starting at 0 and having to do a whole bunch of training epochs before you get to see anything. All right, let's see how the Spark job UI is looking. All right, we have it up. So drivers added. What we have is zip with index, single stage that reads from a text file. Another one just reads from a text file. Here's our first reduce step. You can see, just like I predicted, you're reading from 2 text files. You can do that in a single stage, but once you union them, you have to move out of that stage and into another stage. And then the next stage, you have partition by and you have map partitions, because what you're doing essentially is this whole set of map steps and reduce steps here. If we look, we can see we completed 2 training epochs. Our cost function puts us at 1.45, and our accuracy is very low, 5.8%. And then in epoch 2, we managed to lower our cost function. We're moving along the derivative of the cost function. So what's being minimized here is actually the cost function. Your accuracy isn't necessarily being maximized. It depends on how well you match up your cost function to your actual application. And even if you could maximize your accuracy, there are situations where you don't want to do that because you're trying to avoid overfitting. All right, so basically a lot of the rest of the tasks, because the training epoch is doing the same thing over and over again, you'll see that a lot of these have very similar, they're the exact same setup, but now that we've already unioned the 2 files, that we have their union in memory, essentially, it's cached. So no further stage will need to do that particular section. So they'll be sticking with this linear section where this stage here, where it's partitioned by and map partitions, and moving on. So you can look into an individual stage in the UI as well. you can see it's doing partition by and map partitions just like it said, but your resulting RDDs and your map and your reduced step at the end, they're shown here, but weren't necessarily shown in the simplified DAG visualization when you were looking for the entire job. So essentially, jobs show up here, job UI. It splits it down into, in each individual job, there are one or more stages, and then within those stages, there are tasks. So in a properly distributed system, different nodes would be doing different parts of this work. But essentially, this is how this is going to continue on for the rest of the 100 epochs. It's going to basically continue doing this. So we will just close out of that. But before that, you can see that the first task here, the one that actually had to do reading the text files in the union, it takes a little bit longer because all the future tasks can skip that because we have that cached. They don't take as long. But it's not a huge difference because the bulk of that actual work was training the machine learning model. And this is sort of why model training is your most resource intensive thing, because even if it's just a bunch of the same operations repeated over and over again, you do have to do them a lot in order to actually get any appreciable result. So you can see we've gone through 7 epochs here. Our cost has fallen below 1, but our accuracy is still only 9%. If we let this run for the full 100 epochs, our accuracy might reach probably 70 or 80. The MNIST data set, it's a good thing to use a neural network for because it's not, as they say, linearly separable. You can't basically separate the space, that 784 dimensional space, out into sections for each number. But the neural net sort of fudges that. It knows you can't do that, and so basically it deals better with nonlinearity. So we're just gonna close out of here. I'm gonna take a second to look at the other one. All this does essentially, so we're parsing values out from the file. If you have, basically we're assigning the string values here, any that can be, into numerical values. So neural networks basically only deal with numerical values, except for some cases. Basically, they deal much better with numerical values than non-numerical values. So we set up our data, and then what we're actually doing here, well, first we call a scalar model. It's inside Spark MLlib, and what it does is to make sure that all your features are scaled between some values, usually between 0 and 1, while maintaining, a meaningful mean and standard deviation potentially. And there are a lot of machine learning models that work better if your data is between the values of 0 and 1. So we run a scalar like this. And then we split our data in between training and testing sets. We define our layers. So while the last neural net had 3 layers, an input layer, a hidden layer, an output layer, this one has many more layers. It's 9 input layers versus the others 9 input nodes versus the other 784 input nodes. And then several hidden layers of 5 neurons. And then an output layer of 2 neurons, because this is a binary classifier. So you can do multi-class classification with the same class, but this one only has 2 outcomes. If you go back and you look at the data, you can see that the outcomes here at the end, the labels are either 0 or 1. You feed these layers into your multi-layer perceptron class, which also comes from MLlib. You give it a seed, a block size, set number of iterations. So this one is going to do 100 backpropagation steps, just like the other one. And then it's going to use the multi-classification evaluator, also from MLlib, to get the accuracy metric out and then print it once it's done. We probably won't get to see the end of this model training because, it will also take a while. But if we get it started, we can look at the tasks. In that copy. All right, so this time what we're doing, rather than running the Spark submit with the Python file, we are running a Spark shell with our Scala file using the -i. All right, we got our predefined Spark context and Spark session up. Once it's started, it will create a new Spark context and Spark session, and then it will start processing. So like I said, there are some stages of processing before it actually starts doing machine learning. So things like the data parsing and the scaling and shifting will happen first, and then the actual training will happen after. We can once again go look at the job breakdown for this new task. Starts here at standard scalar. This one's a bit more complicated. It's using tasks like whole stage code gen and object hash aggregate, which the other did not use because it was handwritten by someone who was basically using PySpark manually. So they use the lower down, the most basic sets of operations in order to make this work. So you take your CSV, it's doing the scaling here. And then we've also got stuff like this. So once that is processed, then it moves on to the second processing step where partitions are mapped. Get a count stage. And now you can see we're back at a bunch of repeated versions of the same type of processing. So we started actually training our neural net here. And as you can see, because there's no need to join and everything's already partitioned based on what happened with the scalar and the parsing, then essentially the stages just consist of a set of tasks that need to be done. And so there's no need to have multiple stages inside of these jobs from here on. And you can see that first stage actually did trigger some shuffle, but subsequent stages, since they have the cached version, the parsed and scaled and shifted version of the data already available and partitioned, there's no need for further shuffles during the training, the backpropagation steps. So it's costly, but you can avoid doing it a lot of the time if your data is already properly formatted. that is about all I have for today. This is a good time for questions. I'll leave it running in the background. Uh, but if you have any questions, feel free to either put them in chat or unmute and ask them.
Yeah, I had one question. So I guess this example specifically is for like machine learning, or I guess in a sense is there, do you have the ability to fine tune how the distribution has it, or sorry, how the distribution happens? And would you fine tune it versus like for machine learning workloads and then fine tune it a different way for maybe some other kind of ETL workload, if that's possible?
Yeah, so if you have, say you had the same data on two different Spark clusters, and one is meant for an ETL sort of workload, and one's meant for a machine learning kind of workload. It's definitely possible that there are different partitioning strategies that work best for either one. And you could either, manually define it. If you use repartition, you can define how your data is split up. Or you could just leave it to Spark to repartition when it needs to, and hope that it doesn't have to do it too much in the course of your operation. Or you could potentially design your process, start running it, look at the tasks, and see where it's doing repartitioning and try and minimize that. But as for like the specifics of how you would distribute your data for machine learning versus how you would distribute it for ETL, I think that's a question that like has to be answered on a case by case basis. Like each time you're using your data differently, you have to look at how it's being partitioned.
Got it. Thanks. And then I guess one other question that you mentioned that like when it's storing stiff and it has it in cache, would that be potentially something that you could utilize to optimize the distribution of work over like a distributed like platform or process that you're running? Like, could you ahead of time cache things, or would it make sense to do that to potentially
Well,
optimize
some
your processes?
yeah, sometimes it does. Um, So if you cache a data set, it will stay in its regular partitioning, but it'll be available in memory. So nodes that need to get that data, it's still in memory even after the particular stage has completed, or stage or task that creates it is completed. Um, and it only gets basically garbage collected when the Spark job, the Spark context ends. What was I saying? Basically, yes, you can definitely use cache, especially with Spark's lazy evaluation. There are times where it will, not compute something, and then you'll have to do it later on. But if you were to specifically calculate out something that you need later, and then cache that, and then work off of that result for later on, you can save yourself work, or save yourself time in the.
Got it. Thanks. Alrighty. I don't see any questions from the YouTube chat, and it doesn't look like there's any more questions from the Zoom side. I guess we can go ahead and wrap up. Thank you everyone for joining us for Data Engineers Lunch. We will be here same time, same place next week, but we are looking at a more variable time slot, so we could potentially look at a more worldwide live audience. But again, all these videos are streamed directly to YouTube. So if you're not able to catch it live, they are available on our YouTube channel, youtube.com/AnantCorp. And if you're watching this on live, currently, or if you're watching the playback, don't forget to like and subscribe, and we will see you guys next week. Take care.